And I think it probably asks you on your computer as well.
All right, it does.
Yeah. Good afternoon, everybody, people in the room and on Zoom. It's with great pleasure to introduce today's speaker to you, Dr. Marek Lewicki. Not practiced pronouncing the last name. He's done his PhD in Warsaw, postdoc in Adelaide, and in
King's College.
King's College, and he's been in Warsaw since
2020.
2020, yeah, so about 4 years now. He's now a senior researcher in Warsaw. And today he's going to tell us about gravitational waves and cosmic strings.
Oh, thank you. And thank you very much for the invitation. It's my first time in Dublin. Having a lot of fun so far. Right, so the title is Search for Cosmic Strings Through Gravitational Signals. This is not going to be a very technical talk. Right, so let's start with, let's say, experimental motivation to do any of this, which is, of course, searches for gravitational waves. So what I'm showing here is the abundance of gravitational waves, which is what we typically use in cosmology as a function of frequency. And I'd like to start with this slide because, well, only 2 of those experiments are currently running. This is, of course, LIGO, which has finished its 3rd observation run. And it's running its 4th, and eventually the sensitivity will get down to the design sensitivity. Well, it hasn't seen a stochastic background so far, so for me this is actually a bound. But as you know, it has seen a whole lot of, well, it has discovered gravitational waves for the first time, of course. It has seen a lot of collisions of astrophysical objects, so it did it had a lot of discoveries in its running time.
This is LIGO.
Yes, this is LIGO, Virgo, and Cargo, but if you just say it's LIGO, they'll send you an email saying it's technically the LVK collaboration, which is why
Can you remind me where K is?
Kaga, that's in Japan. This is the one which
is that the one that's in the Tamir Panda mine?
I think so. Yes, so they've joined the collaboration. I think they didn't really have that much sensitivity yet, but they are catching up to LIGO and Virgo right now. And they maybe will participate in round 4. I think they're not doing that yet, but maybe. But we'll see when the data comes out. That is going to be maybe next year. Right, that is one of the running experiments, and then the other one, it's actually an array of experiments. Pulsar timing array. The one that I'm showing here is the result from nanograph, which is, well, for historical reasons, I've always been using nanograph data. There are actually several collaborations. So there's the European pulsar timing array, and there's the Parkes pulsar timing array, and finally nanograph. Right.
These are indirect because you're not observing gravitational waves from those, you're just inferring their existence from this blowing of the pulsar.
Yes, that's true. So that's how the technology works. So maybe let's actually go through this tiny little bit. Right, because the reason for this slide being here is to say that the future looks bright and optimistic for gravitational waves because we'll have a whole array of new experiments in the future. So firstly, next generation of terrestrial laser interferometers, the one I'm showing here is the Einstein telescope. So this is the European project. As you see, it will have a much better sensitivity than LVK does. It's not completely clear when it will be realized, but late 2030s or 2040s are possible. So then, if we are trying to lower the frequency for our sensitivity peaks, we need a longer interferometer arm, which means we launch into space. So this brings us to LISA. This is probably the most established of those future experiments because you might have heard that LISA was just adopted by the European Space Agency in January, which means that now the commissioning of the experiment will start, and we're, well, as sure as we can be that it will actually be realized in the 2030s. So LISA is also well on its way. And then when we're trying to produce an even longer interferometry, we end up in pulsar timing territory. So indeed, this is not, well, essentially you're right, we're using the pulses from the pulsar to try and infer the distance by Doppler shift. This is what the experiments are doing, but they are able to check whether it's gravitational waves or just noise, because you expect a certain spatial correlations in the Huggins-Dawes curve, which is characteristic for gravitational waves, and this is why there is now some evidence for the signal actually being gravitational waves, because there is already evidence that there is HD correlation. This is not yet certain, but it's, I think, around 3 sigma strong evidence that this thing that I'm showing here, this is actually a parallel fit to what the data is showing. So the line going through here would fit the nanograph data at 1 sigma if it's in the continuous column, and at 2 sigma if it's in the detachment. Right, but there's some evidence already that this is due to gravitational waves. And then, yes, I also should say that there are, of course, future experiments on the horizon. So there's the SKA, for example, which is being developed right now, and then as years go by, I still plotted sensitivity. Of course, it's not going to see this parameter space, it will just have a much better handle with the signal, which is down here, if the signal, if the discovery is confirmed. But in the meantime, well, of course, all the existing collaborations will keep on taking data, and we will have smaller and smaller error on this. Actually, the evolution of this error is something that I will tell you a little bit. Okay, so.
Is there any interest in building experiments that can probe the 10 to the minus 6 region?
10 to the minus 6. Oh, yes. Oh, I forgot. So, yes, there are some experiments here, but this is something. Oh, so as you see, this is something which has to be larger than the solar system, but smaller than the galaxy. What is being done, so the one example that I have here is Roman, but you can reach to lower frequencies, so higher frequencies, also with astrometry surveys. So essentially trying to tell distance of the stars, not necessarily pulsars, and inferring whether they're moving in a pattern that would connect with gravitational capacity. So there are some experiments, but the problem with them is, well, even when trying to plot this curve, I wasn't quite sure if this is the right sensitivity, because well, those experiments their aim is not to look for gravitational waves. This is a secondary study that we will do later on. And it's very unclear how much let's say, the errors on your measurements will break this. As you know, this is something which is very sensitive to how well you can measure the distances. Yes, so this is one of the lines, but it could be also significantly better sensitivity, but it's very difficult to tell at this stage how those sensitivities will actually look like. Some people are very optimistic, and saw curves that go all the way up here with Gaia and Thea, but I'm not as optimistic about those. So, but there are experiments, yes, there are planned. And I should also point out, yes, that there are ion and edge, which are, it's a slightly different experiment, so those are both laser interferometers. In ion and edge, what is done, well, those are using cold atom technologies. So you're not shooting a laser between two mirrors, as you usually do in an interferometer, but you're still shooting a laser between two mirrors, but there are also bunches of cold atoms in between, and then you do interferometry on those cold atoms to measure the state. And this is the way to infer the distance between the bunches. So this is a slightly different technology. This is why well, it operates in a slightly different frequency range also than LISA-ET. Actually, the point of it is to try and measure in this blind spot between LISA and the telescope, And ion, so ion is the terrestrial version of this experiment, while EDGE is the version that could be launched on a satellite. So the status right now is that ion 10 is being assembled in Oxford, or at least there's work being done for it to be eventually assembled in Oxford, which is a, say, proof of concept for this. It didn't quite make it out, only ion 100 would. But there is also a sibling experiment called MAGIS in the US, and they are already building a 100-meter version in Virgo. Right, maybe I should say that the name stands for Atom Interferometry Observatory and Network, with the word network implying that the idea is to have a bigger network of those experiments, because once the technology is developed, it should be relatively easy to produce more of them and have a better coverage. Right, okay. Right, but the main message is, of course, that there are very optimistic prospects to measure a whole lot more of the frequency space. And as you see, well, both of the experiments we have running are making great discoveries, so this is something that's looking very optimistic. Right, but the talk today will actually be about cosmic strains. So one of the possible sources in the early universe of gravitational waves. Right, so to start with the basics, what are cosmic strains? Well, stable one-dimensional topological difference. That's not, I realize that's not very explanatory, so well, we'll see how they can appear in the early universe. So the possible origins are, well, there are a number of different possibilities. For example, predictions from superstring theory and for disk strings, those are quite popular. But I will not get into those too much. Well, I'll mention them later on again. But probably the most natural explanation, at least the one that I like the best, working on particle physics, is vortex-like solutions, because this is just field theory. So essentially what we need is a spontaneously broken group. Right, yes. So something very simple, but that is a scalar. The potential looks like this. So it's U1 symmetric, and the minimum is not at 0. Simply something like this. I'm sure you saw this at some point in the past. And of course, as you know, the point is that the field needs to roll down to the minimum once the symmetry is broken. And well, you of course know that everywhere in the, well, all the minima are equivalent. Locally, it doesn't matter which one you choose, but globally there is a difference. And to see how that comes about, well, we make a drawing like this. So the field chooses the way, well, let's say the arrow indicates which way the field moves. If something like this happens, then in disconnected regions, so those are, say, small horizons in the early universe, if the field does something like this, you see that when they come into contact, there will be a problem here. All the arrows are pointing away from here, meaning that there will just be a jump in the phase, and that cannot, of course, happen. It would have a very large energy, and indeed it does. So what happens when a situation like this occurs? Well, we can find a solution for this. Of course, it's not really important what it is exactly, but the point is that in this one point in the middle of the previous plot, what you find is that the field simply has to stay in the unstable configuration. So there will be a whole lot of energy stored, and that, of course, corresponds to a cosmic strain sticking out of the white in the previous slide. Right, the main important thing that we can learn from this is that the tension of the strain, so the energy per unit length, in this configuration will be proportional to the curve of the field breaking the symmetry square.
You said in one of your slides that, as a definition of the cosmic string, was a stable topological defect.
Yes.
But it could be decaying as well, right?
Well, it cannot. No. Once you produce this, it will remain, because due to flux conservation, you cannot get rid of this. Right? There is no realignment that you can make for this discontinuity to be gone. It is
Energy cannot in any way be damped.
It can be done, but that will mean you cannot get rid of the strain. You can only, it will strengthen itself out, is what will happen. But indeed, this is stable. So the strain cannot just end. This actually goes on for, due to flux conservation.
And at what point do you get a gravitational wave from it? It's not just from the existence of the string. Is it the formation of the string that you get the gravitational wave from?
I'll get to that. That's what the next couple of slides will be about.
What do you need to, what can the string end on? What can the string end on?
What can the string...
If I have some, I should be able to end it on some type of particle. Is it?
Well, no, in the... Go to the next slide. In empty space, it cannot just end. The other thing that, if you do that in 3D, the only thing that can happen is you can have infinite strings that simply go out of the horizon, or you can have closed loops. So all those little dots are actually closed loops of string. But it cannot end. So this is something that you will see when the phase transition happens, when the U1 is broken in your universe. Then, of course, the next question is, what will happen with that? What are the implications if that had taken place at some point? So, what would a cosmic string network do? So, well, in the simplest possible situation, if we're only thinking about long strings, they're not moving very fast, they would just redshift as a to the power minus 2. Effectively like matter, but of course stretching a string doesn't do anything, so it's matter with one less dimension, a to the minus 2. And that, of course, would be terrible, because then that would mean that they tend to overclose. Well, they would tend to dominate the energy of the universe, and we know that strings are not currently dominating, so that would be terrible. But luckily, due to non-trivial dynamics, we are safe because, well, non-trivial dynamics. So strings, whenever they collide, they intercommute on collision. Meaning that if you have two long strings that hit each other, you will end up with less long strings and a closed loop. Well, I don't want to show you the exact equations, but once you take into account this as an energy loss mechanism, it turns out that this whole system is going towards a stable, so-called scaling solution in which the total energy stored in the infinites of very long strings is just proportional to the total energy at the time with some coefficient, and that coefficient is just the string tension, so mass per unit length times Newton constant. So this is a very small number, and it indeed turns out that this is safe and it doesn't break anything. Strings could have been produced and we could not even know about it.
By the way, if you have a closed string, can it shrink to 0?
Yes, that's exactly what I want to talk about in the next slide. So, of course, the next question is what happens with the closed loops, because in the previous slide, I only told you that if the loops are being produced, we lose energy, but then we don't care what happens to them. Now, what does happen is after their creation, so this is already a very simplified model of this emission. But essentially, in this simple model, what we're saying is that this is the length of the loop, it's time t. This is ti is the moment that it was produced, so cut from the network. So it's cut from the network with alpha being its initial size, a fraction of the horizon that the initial loop has. And then it will just continue to lose energy. This gamma is its total decay rate. Well, it's of course proportional to the Newton constant times mu. And as you see, there is just t minus ti, meaning that it will continue to lose energy with this rate until this drops to 0, where it has no energy and just disappears. So this is, of course, well, this would require further explanation. Here I, of course, assume that the energy is only going into gravitation. So that's why the coupling here is G mu. And then the only thing you do is you know that the loop has a very large energy, it will begin to oscillate, and you just sum the energy emitted in each of the nodes, and that gives you this parameter gamma. This one we were going to be around 50. A very long time ago. Right, so you might wonder if also particles are being produced, but in what I'm talking about, I will mostly be thinking about gauge strings, meaning that the symmetry that we broke early on was actually gauged. And so, specifically since we're interested in times much later than the actual time of the symmetry breaking, it turns out that the emission of particles is suppressed because, well, the gauge bosons are very heavy. So you need a lot of energy concentrated in one piece of the string to be able to produce this one very heavy excitation. And in later times of the revolution, the strings are, well, those are objects that are, as you see, the sizes are, say, 0.1 of the horizon, so those are huge things. They are relatively straight, so locally they don't really have enough energy to produce gauge bosons.
So can you clarify just what model you have in mind? You just showed us scalar electrodynamics.
Yes.
Which is not a model in the union. It's not one of the aspects of the standard model, for instance.
Oh no, you need something beyond the standard model.
So yes, okay. So you're assuming that beyond the standard model there is some scalar electrodynamic type of field.
Yes, that there is a U1 symmetry broken at some point. That is the minimal example.
There's no evidence for that.
Well, not yet, but we're getting it. That's what the
Okay.
no,
Clarifying. It's
no, there isn't. That's
a proposal for something beyond the standard model.
yes, this requires new physics.
Why do you take alpha 3.1?
Oh, that's right. So this was quite recently. Some people would tell you up until today this is a big discussion because this is something you have to get from numerical simulations. Essentially, what one does is you start from the box that we had in a couple of slides back. You simulate the whole network. Then you try to check where the energy is actually stored, and you find that most of the energy is within those long strings that have 0.1 with sizes roughly of 0.1 on the horizon. There's a whole lot of smaller strings as well, but they don't carry as much energy. And this, well, as you see, those papers are not from that long ago. They did for a long time. People treated this as a free parameter. Well, some people still do, but I believe the simulations, and if you believe them, it's fine.
And the simulations were done in what context? Again, just scalar electrodynamics.
Oh no, those simulations are not Virgo. So you already assume that these are one-dimensional objects with some energy density. Those are more simplified. Actually, this is also...
You're saying they don't depend on the height of the potential?
No, because you just assume that you have a one-dimensional object with some energy density on it. They don't take into account any of the underlying modeling. So this is very simplified. In fact, well, this is another ongoing discussion, because if you try and put scalar electrodynamics on the lattice and try to see if you will develop a cosmic string network, you will find that you don't. Well, I mean, you do, but not like this. You will never see this happen. In fact, what you will see is that there are no closed loops because they immediately decay into particles. But the way to reconcile those two approaches is just that very early on, when you produce the network, of course, because of course lattice simulations cannot run for a very long time after, you cannot have a separation of scales. So we're only operating at the scale in which the breaking of the symmetry occurs. And then, well, as I said, you can have...
That doesn't sound right.
Right? That doesn't sound right?
Because you can set up the problem so that you are already in the broken phase. You don't have to.
It's actually not that simple. So you can try to set up the parameters, but you will always have problems because the hierarchy between the scales is that there is a... If you're trying to do a lattice calculation, you need to be able to resolve how the string looks like. Right? So you need... you need sensitivity at the scale of the width of the string. But in a cosmological context, the width of the string is completely negligible. If today alpha is 0.1, then I'm talking about a huge object, but its width is of order of 1 over 10 to the 10 GeV or something. So it's absolutely tiny. There's a huge separation of scales. And this is something you cannot deal with in a lattice simulation. That's why, well, now we've got a simplified simulation, which already assumes a one-dimensional object with no width. Are the way to go.
But already assuming the scale that the symmetry breaks doesn't make it model dependent?
It does, but this is the one moving part that we will have throughout, as you'll see. Right. Right, moving on. So, what I should say is that, of course, so this whole energy is the shrinking is, of course, going into gravitational waves, so then you end up with a relatively simple, let's say, energy conservation type of argument, where you just integrate the energy produced by those decaying strings. You have to know, again, the loop density and so on, but this turns out to simplify quite a lot, and in the end, you just have to deal with one integral, which is, well, the amplitude of gravitational waves ends up as a prefactor. And then we have just appropriate redshift factors for the frequency and 4 powers because of redshift stuff radiation. And we have the redshifting of the loop population itself. As you see, there's nothing super complicated. The only thing that goes into this from this very complicated numerical modeling is this one bit coming from the density of loops that you need to find by simulating the entire network. But this ends up just being a number, which depends on the expansion rate of time here. So from this very complicated picture, you end up with something relatively simple. Right, and then of course this will be the final abundance of gravitational waves that we will see today. And this is how it would look like. So indeed, you're very right. There is one moving branch, which is the level of the breaking field, or the GeV energy scale of the strings themselves. And this one is going to show you roughly what scales you should be thinking about. So GeV 10 to minus 10 or 11, which corresponds to valves of 10 to 13-ish, and down to GeV 10 to minus 17, which corresponds to a valve of 10 to 10. And then, so what would happen if the valve was smaller? Well, gravitational signal is smaller, we will not see it likely, and then this whole story. It's less interesting, at least from the point of view of gravitational waves. So you see that we're thinking of scales which are relatively high. This is not the first thing you'd be thinking of trying to extend standard somehow.
If you were thinking of Maxion models, would this apply to that?
It would, but quite differently. Because with axions, as I said, when I'm thinking of our gauge strings, if you're thinking about axions, the story is quite a lot different because then, well, you can produce axions all the time. Meaning that the strings, they're not just moving freely and only losing energy from gravitational waves, they are mostly producing axions. So indeed, people do simulations quite similar to the ones that you would do for gauge strings, for axions, but then what you're trying to find is not gravitational waves, but how many axions you produce and what's the contribution to dark matter density that would be. So it's a similar story, but going in a different direction.
Could you briefly show the previous transparency with the formula? Yeah, where is the frequency dependence except for 1 over f on the left at the beginning of the product?
Frequency dependence? There isn't one, I think.
Yeah, I see 1 over f and nothing else.
Yes.
But your curves are not 1 over f.
What is that one?
The curves, the prediction you have shown on the plot is not reverse frequency. It's Morse, well, completely different picture.
Oh, of course, because yes, for each f, you have to do this whole integral.
So everything is frequency dependent here.
Yes, that is.
Okay, and you have no details about what the dependency could be.
I do, but it's quite complicated, and
Okay.
I'll tell you about it later on.
Thanks.
But yes, it's not.
So sorry.
Oh, no problem. Please feel free to ask questions at any point. Well, right, so the next thing to say is that once we have the signal, we can already start fitting it to the data. So initially, when the first nanograph data came out, that was the first one, but wasn't entirely negative from pulsar timing. That was 2020, I think in September, nanograph 12.5-year data. Well, I'll show you a little bit more about the data in a second, but well, back then, I was very optimistic about it because it turned out that cosmic streams are actually a very good fit. So the data would be somewhere here, but I'm already showing you a fitted result. So spectra like this, the continuous ones would fit this whole data up to 1 sigma, and the dashed ones up to 2 sigma. And indeed, they fitted the data better than supermassive black holes, which was very nice. But sadly, it didn't last. So this paper came out a couple of days after the data would appear. But then subsequent updates. So again, I'm only showing nanograph data, historically, right? But there are also other pulsar timing collaborations.
So can you remind me, what is nanograph again?
Nanograph. So this is one of the pulsar timing array collaborations. This is the North American. So it's mostly in the US, but there's also the European pulsar timing array, and then there's the parts pulsar timing array in Spain. Right. Okay, so what this plot is showing is that this is the kind of plot that you are likely to see in pulsar timing papers, because when doing the data analysis, it's much more natural to use parameters that I would not typically go for, which are this amplitude and spectral index, which in our way of description just converts to A controls the amplitude, and then there is this spectral index, which is minus gamma, meaning that gamma equal 5 is a completely flat spectrum. Right, but the point of this plot is to show you that back in 2020, this is how the nanograph data looked like. This is one sigma fit and then 2 sigma fit. And if we think of our cosmic string spectrum as a power law, this very small frequency band where we had the data, it would show you, it would end up looking something like this in this plot, approximated by power law, where color shows you the G. So you see that it's fitted within sigma and fitted better than supermassive black holes, because in the simplest model of supermassive black holes, when they only lose energy by, well, when they spiral only due to losing energy into gravitational waves, they have a fixed slope, which is 2/3, which with this strange index ends up being exactly here. So they were actually a better fit than the simplest of models of supermassive black holes. But unfortunately, so then there were updates from other pulsar timing arrays, which looked nothing like this. They actually looked more like the current data. And then, of course, last year there was a next batch of data which was analyzed. But I would say this is the main point, that the analysis keeps on improving. And what we end up today with today is this thing. So this is, as you see, the slope is much bigger. 3 means that f to power 2 would be a reasonably good fit, and a higher amplitude. So unfortunately, you see that our vanilla model of cosmic strings doesn't go anywhere near that. It's not a very good fit.
We needed a supermassive black holes.
Yes, that's a good point. Yes. Well, so actually, if you draw a 3 sigma line, I think it ends up being roughly close to the simplest supermassive black hole line. But it's true that with supermassive black holes, they are already announced. I will mention this a little bit at the end.
That's really very simplified picture for the supermassive black hole.
That's true. But it's also true that I don't think we have a very good one. In the sense that so people, there is a phenomenological model that people use. I'll show you how that looks like later on. Right. So, well, the problem is quite straightforward. This is the amount of gravity. Just remember from the first slide that, of course, if we plot our simple spectra, it's then it's simply too flat because we're close to the peak.
The other thing, your line for the supermassive black hole, I would have expected a dependence on the mass of the black hole.
There is, yes, but the mass only changes the amplitude. That's why it's a line. So the mass gives you the amplitude, or the abundance gives you the amplitude. But
Why does it only
slope-
change the amplitude? Why does it only change the amplitude? I mean, how the system radiates should be quite sensitive to the mass.
The mass. I don't really remember the exact argument, but you can actually show that in the simplest model, where you're only then using gravitational waves, the slope is always 2/3. And it's not even supermassive black holes, it's any, say, compact object. There's this paper by He, perhaps, that people always cite for this. It's a very, it's a pretty general result. Right, okay. But then, so what can we do? There are a couple of things that you can do to make the model more complicated. The one we went with is to kind of cosmic superscales. The word super, we actually only used it in a very phenomenological sense, because the problem is, so this is essentially a non-minimal model.
Sorry to keep on doing this. How does the pulsar timing, I mean, what is the model that's going on for the cosmic ray setting? You have a pulsar that you're imagining is actually a cosmic ray rain that is slowing.
Yes.
So the pulsar usually would be associated with a magnetic field trapped in the star remnant, but now you have a magnetic field trapped in some sort of cosmic string. I'm just trying to get the picture in my mind of what is supposed to replace the picture I have for a pulsar.
But why do you want to replace the picture for a pulsar?
Because the picture for pulsar is slowing down. I mean, it's a pulsar, so it's meant to be a star that has collapsed, and it has got a magnetic field there, and the reason it's slowing down is by gravitational radiation. That's the picture I have in mind. Whereas if I'm going to replace that and say that actually what's going on is a cosmic string that's gravitationally rotating, I want to see where the pulsing is coming from.
The single pulsars are not slowing down because of gravitational.
Yeah, yes.
You need binary pulsars.
Yeah, because for those experiments, we only treat them as a regular source, so they keep producing pulses.
Well, the key point is that I need a magnetic field of some sort. I need something that is flashing radiation at me as
Yes.
it passes, as the direction goes there. That's usually in my head is a pulsar that's rotating.
But that would be
Maybe going
electromagnetic
away.
energy.
Sorry,
Magnetic field will produce electromagnetic energy.
but that's what you get. That's what you see. That's what the pulse is.
True.
The pulse. I don't see the electromagnetic energy at all here. That's my problem. I just don't see what's pulsing and why it should be pulsing.
Particularly for the pulsar timing story, the only thing we need is that they are regular. We don't even, right? Because we just need to time the pulses.
Yes, but I want to have some understanding where the pulsing is coming from, or what is pulsing.
From a pulsar.
You are replacing the pulsar by something that's now that's now a cosmic string. as far as I understand.
No, in the so just to have this measurement, I'm not replacing anything. I'm just thinking, so there is a pulsar, I'm timing the pulses, and it's just
Where is the cosmic strain?
so far nowhere. I'm just timing the pulses that are in regular intervals, but if the distance with the pulsar is increasing, the intervals will be slightly longer.
Yes.
That is the only thing that I can hope to measure.
Yes.
And that is where all this data is coming from. We're only checking whether the pulsars are moving away from us. Because the point is,
You're not going to give me any explanation as to why it's pulsing.
as to why, well, that doesn't have anything to do with gravitational waves. That's just,
No, it doesn't. I mean, well, it does in the standard picture.
yes, but this is, I'm only using the very standard picture for pulsars. Nothing non-trivial is happening to pulsars. It's only their distance between us and the pulsars that is changing due to gravitational waves. So
It's not the distance that's changing. It's that this means that they're slowing down.
no, it's the distance that is changing. This is a Doppler effect. So essentially, I mean, can I draw something? Oh, there's a chart. So that's
These
what
are these very fast pulsars.
yes. But the whole point is that if we have so there is us and there's the pulsar doing its pulses. Well, you'll see something like this. If it was moving away, you will see that those are longer. Right? This is the only thing that we are using for this.
Alternatively, if it is slowing down, then the pulses, there's a longer interval between the pulses.
If it was slowing down, yes, but that is something I think
That's my understanding. Am I missing something? That's my understanding of the way that the pulsars were supposed to be slowing down. And the gravitational radiation is coming from the fact that there's probably a binary system here that the pulsar is rotating around. And that system is gravitationally radiating. Because it's radiating, the system is slowing down, and the distance between the pulses is
Yeah, I
changing.
think that's all true. I think when on top of that, he's trying to put a primordial gravitational wave spectrum on top of all that.
Yeah, he's not trying to say, there are no
What you
pulsars.
say is absolutely right.
Yeah, but he's not saying that,
But in addition, suppose there's a background gravitational radiation from,
yes.
I guess, the cosmic strings. What would that do to the picture?
Oh, I see. There's some ambient background.
Yeah,
Exactly.
and that's
Oh, I see.
coming from the
You didn't say that, so I didn't get that.
That's what I was getting towards. So the way I understand it is that if you have a pulsar, well, it's shooting, its ray in a direction, but it's also rotating. That's why we see pulses every now and then, because the axis of rotation is not the same as its emission axis. So we just see it blinking, right? But when it's moving away from us, the distance between the pulses is
Sure, no, that's fine. I just, if it's an ambient background of gravitational radiation that you're trying to explain and use that to fit a data, then that's fine.
yeah, that's exactly right. Right, and this is where the Helling-Dawes curve is coming from. Because if you have a plus, so if you have two pulsars, the other one would be here. If this one is going away from us, then this one should be coming towards us, right? And this gives us an angular correlation, or spatial correlation, corresponds to HD, which they are now observing to some extent. Right, but yes, the gravitational waves that I'm talking about are ambient, they're everywhere, so this is a background that is everywhere.
I understand. The reason I was confused is because the standard evidence for gravitational radiation was slowing pulsars before LIGO.
Right.
That's still intact.
yeah.
I thought he was going to
Yeah.
explain that.
no.
No,
yeah.
no.
This just made no sense to me.
Right.
Okay. So
do I understand this correctly that at higher frequencies, the abundance of your gravitational waves does not really change?
At higher frequencies, yes. Oh yeah, I'll get to explaining that a little bit later on.
Okay.
So what I'm trying to say here is well, we need to have a non-minimal model, but unfortunately, so with superstrings, what you expect is that the intercommutation probability will be smaller than 1. But this is something that is unfortunately very non-trivial, in the sense that it hasn't even been simulated numerically, and that is simply because, well, it's more difficult. Even the standard cosmic strain simulations, as you saw, they were developed quite recently, and that assumes intercommutation probability of 1. If you lower the intercommutation probability, then the strings will just miss each other most of the time. So you need to wait longer and longer for the network to develop into scale, meaning that you need a much bigger and much longer running simulation, which is just more difficult, and it simply hasn't been done. Well, but to still try and do some phenomenology, the very simple scaling that we expect is that the abundance or density of strings will simply go as b to minus 1, and then that will translate directly into the abundance of gravitational waves. So it's a very, very trivial model.
So when p is much smaller than 1, meaning that they're just not intercommunicating.
Yeah, so in this simplest picture, they just don't intercommute, so there's much more of them when they enter scale. And this, well, it bumps up the radiation wave spectrum as well. So this whole mess of lines is the lines we had before, but now for each of them, so 10 to minus 12 p1, 10 to minus 12 p.1, 10 to minus 12 p.01, and you see that this will help, because this is the 10 to minus 12. If we can just increase the amplitude with this other parameter, you see that it looks more like the data that we have at hand. But indeed, when you do the analysis, slightly better, use the actual data, and fit the exact shape, we find that there is a reasonably good fit, and indeed, G mu 10 to minus 12, roughly, and intercommutation probability is less than 10 to minus 2, so this is 1 sigma fit, 2 sigma fit, 3 sigma fit. Now, you can also see that there are LVK lines, and we'll get to why these are here in a second, but there are also these 5 points, which are the 5 benchmark spectra that I will come back to in a second. Because, of course, now every spectrum, well, the shape and amplitude in the simplest model is just given by those 2 numbers. So, well, the point being, the plane here already corresponds to the entire spectrum.
So this must be a very high frequency, right? That's where the LVK sensitivity.
Yeah, exactly. So that's where the flatness comes in. But before we go there, so this is the actual data and the 5 lines that we had. Well, the spectrum corresponding to the 5 points. Maybe let me try and tell you why the fit changed so much over in a relatively short time span. And the reason is that in the previous data, so the 2020 ones, I think only the first 5 pulsar, the first 5 bits were used, because the other ones were mostly dominated by noise. It's actually true that there are more bits, and they are even more dominated by noise. So if you try to fit spectra to all of them, you will end up with something which is very steep. But we know that to be incorrect, because at higher frequencies, you have more noise sources that can still masquerade as. Well, they wouldn't really masquerade as gravitational waves, because when you try to compute the Helmholtz-Downs correlation, you will see that it's actually lowering it instead of making it higher. But if you just use all the bits, you run into trouble. And so this initial analysis, which is very simplified, just assume that all of this is not here, and we only have those first 5. And you see that with the first 5, a straight line is a good fit. So a flat spectrum was a pretty good explanation. But now when you take more frequency beams, you see that there's this one, for example, which does not allow a straight line anymore. And this is the reason why now the data prefers more steep lines. Right. Right. But coming back to strings themselves, you remember that the green one is the one that fitted best. You see that this is also the one, well, it's the most steep, so at higher frequencies, it will have the highest amplitude. This is why we run into problems with LIGO. So again, those are the same lines. This is why I showed you the zoom, because from this mess it's difficult to tell. But this is the pulsar timing data from Lewicki. But the lines are the same. Indeed, the green one you see is the one that just barely misses LBK. You can have a higher amplitude, but then you will just be excluded already. Right. Okay, but on the other hand, well, you see that all of those other future experiments will definitely be able to probe those spectra because they're quite, they're very broad. So maybe let's try and test this, because there is well, I heard before people saying that, well, but this is something that happens in the early universe. You can put in some extra craziness that we are not able to measure so far, but you can maybe hide from the future experiments. And this is true to some extent. For example, the dashed line I'm showing you correspond to early matter domination. So let me show you how this comes about. Right, so on to where the spectra are actually coming. This is still the standard one, specifically the one for geometric 7 that we've seen before. But now when we separate the emission into the part that was produced relatively recently, so in matter domination, this is the blue one, and then much earlier on in radiation domination, this is the red one. So you see, as you would expect, that in radiation domination, you end up with a completely flat spectrum. And this is something you can imagine, because as you remember, in scaling, we're essentially pumping in a constant amount of energy all the time from this lone string network. And then the background redshifts exactly the same way as the universe does, because, well, gravitational waves redshift exactly the same as just M, or radiation. So in radiation domination, is completely flat. If we have something like matter, which redshifts slower, then the longer the matter domination persists, the smaller the background would seem to look for us. So and this is actually where this small peak that you see on the left side is coming from. If matter domination lasted longer, this would keep going up. But of course, then there is delay, so we cut emissions. Yeah, we don't see strings from the future. Right, but this is what produces this spectral shape. And then you can, of course, imagine that if something strange had happened in the early universe, it would change something here. And this is exactly what happens. So let me show you a simple example. So you just think of the simplest model in which the expansion, due to some means, changes at some point. So in the simplest model, we just say that the energy density is the LCDN one from some time delta t, but before that, it's scaled as a to the power n. So of course that means standard radiation domination is 4, early matter domination is 3, n equal to 3, and then there are faster scaling solutions, for example, so-called chination, so oscillating scalar field, would give you n equal to 6. But this is something, so there are of course experimental downsides. This has to end by the time when the temperature is 5 MeV, because then we have data from Big Bang nucleosynthesis, and we know the universe was radiation dominated at the time. So there's a cutoff after which we have to go back to 1. Right, but what impact would that have? Let's not go through the derivation too much, but essentially, as I said, if you turn on matter domination, you'll see that the spectrum is falling because the background is much slower than the expansion of the universe is slower than the expansion of your background, of your gravitational background. If we turn it on at 5 MeV, so this is as low temperature as it can be. This is how the spectrum would look like. If we do it at a higher temperature, so say 5 GeV, we see that this departure from the standard line occurs later. And indeed, one can check that the frequency at which something happens with the spectrum, at which we see a feature, goes linearly, roughly, with the temperature. Meaning that if I increase the temperature by an order of magnitude, we will just see it in an order of magnitude frequency. And then, well, in the other situations where the expansion is faster, or the dominant energy constituent is redshift faster than the gravitational waves, for example, as inclination, and you see the spectrum go up. Well, it will be good for experimental prospects, but it's not what is of interest for us just this moment. Right, because what I mean to say is that if you were trying to hide this high frequency signal, you can try and do that, but assuming that there was, for example, an early matter domination, which ended at 5 GeV, so this is as much hiding with this method as you can possibly have. Simply because you cannot move them, so this is what the dashed lines show. This is matter dominated versus normal for the exact same plasma source spectrum. And you cannot hide it more because that would mean you will spoil the deviant data. So the conclusion from this is you can hide from LVK, but not from anything else. Right, but then we can still take this one step further, which is, because this is not the biggest modification that we can have, I should talk about this a little. It's a tiny bit technical, but the idea now is, well, what if we produce the network during inflation, so it endures some amount of inflation, because this is probably the most hiding that we can try and have for the network. So this slide is there to show you that the spectral shape will actually not change necessarily. Now, the reason for that is quite technical. If we're trying to compute the spectrum, what we're really doing, so this gamma equal to 50 that I showed you before, that was actually the total power of emission. What we're really doing is we're trying to sum up emission from all the various modes in which the string can produce gravitational waves, which ends up relatively simple because it goes down to summing the initial mode but at different frequencies. So there are contributions from higher modes, larger k, but we use them at lower frequencies, and then it looks exactly the same as the first mode. So essentially, we only need to compute this one, but then we need to resum through all of the emission modes, and it essentially comes down to essentially doing a sum of the spectrum to the left, but with this weight, which is k to minus 4 over 3. Which is, I know it's a little bit too technical, but the point is that when we're doing this, no matter what I do to the cosmic string network, for example, in this, for those lines here, this is one of the spectra from before, I believe 10 to like 0, 10 to minus 10. I just cut the network, so it simply had not existed before a given time. It did not emit anything. And so you see that there is a relatively quick cut. But when I do this resummation, so yes, more and more nodes, you see it ends up giving us a relatively flat spectrum again. And that is just telling us that, well, even if we cut the emissions at some point completely, it's smaller features of the strings that will exist later on will still dominate. So the reason we see a relatively flat spectrum is that those strings that people are mostly producing here also produce this small tail due to well, those higher emission modes that we need to be summed. It actually turns out that the power law here is minus 1 over 3. That depends a little bit on this current essentially. But this is the most standard model for cosmic strings, and that gives you f to the power minus 1 over 3. And the inflation will not change that. So the question is, will it change anything? And to that, the answer is yes, because for non-standard constituents dominating, that has to end by 5 MeV, right? Otherwise, we will know that's happening with one. But if we submit our cosmic string network to some amount of inflation, this bound goes away completely, because what happens is, so inflation is going on here, for very small scale factor A. The network is produced, so none of those nice dynamics that we talked about will actually take place, because, well, the horizon is effectively shrinking, meaning that the strings will not be interacting with one another. Their correlation length will go out at the horizon, which means that the dynamics are trivial, and indeed they will only scale as A to -2. Because in this, well, we're zooming in, so in this very small horizon, the only thing we see is a straight bit of string sometimes, and no dynamics.
So you're not, the heating temperature is still 5 MeV?
No, it doesn't have to be. Well, I'm not saying anything about the reheating temperature yet. In fact, the reheating temperature doesn't change anything in this story, which I'll try to convince you towards later. But what I'm trying to say is that if you think about what the strings will be doing in inflation, the answer is nothing. Because as I said, even if we start with this, you remember the box with all these non-trivial things going on. If the horizon shrinks, what you will see is just a straight bit of string, no dynamics. So then they will just redshift as if they were doing nothing, which means A to -2. Or however long the inflation lasts, then at some point the inflation will end, so there will be reheating. The strings are still far outside the horizon, they don't know anything about this, but they will actually start to now, their density over the total will be going as A to +2, because the background is radiation. So now they're redshifting 2 powers slower than the background, so this is why this plot is symmetric. First you dilute them, then they start growing back. But all the non-trivial things that I described up to now will only start happening here when they go back into scaling regime. So finally here, the correlation length of the network re-enters the horizon, the strings know that there are other strings, they begin to interact, and something non-trivial happens. That's why you see that first there's a little bit too many of them, and then they go back into it.
So you could say basically this part of the plot is very much like the P much less than 1.
To some extent, but what I'm trying to say is that the only thing that really matters in this picture is when they will come back into scale. Because this is when the emission will start. This is where you actually produce the first loops, and this is when they will start producing gravitational radiation. But because this is all happening in the background, they never dominate, you can have this happen as late as you want. You can have it not happen, so they could still be growing back today, but of course then the gravitational spectrum will be killed. But what I'm trying to say is that, so you see A goes to 1 here, and you can have this as late as you want, there's no bound, and it will still look as if, well, in a sense, random domination lasted up to this point, because the spectrum will be suppressed at earlier times. Meaning that we can effectively kill off the spectrum at even lower frequencies. This is what we're trying to do here. So we're starting with the green spectrum that we had in the plot before. This is the one. So I'm giving exact numbers here, but this is not important. As I said, so here the theory heating is a TeV, which you will think is weird. But as I said, this doesn't really matter because the 2 parameters are degenerate. This is just an example. So if I said that theory heating was 10 to the power 12, but then I increase the number of equals appropriately by, I think, roughly 30, so that would be 52, the spectrum will be exactly the same. Because there are 2 parameters describing only one important thing, which is when the strings re-enter horizon. So actually the reheating temperature is whatever you want it to be. It can even be the primordial inflation, but then the number of equals you end up with has to be a little bit lower than the total number you need for the flatness. What you require from primordial inflation. Right, but the point of this is that you can try and play this game by diluting this spectrum with more and more inflation, which will give you, well, those bluer and bluer lines. So you see we're going towards, you are trying to hide the spectrum better and better, but at some point, you will just break the fit, because you see you're starting to modify the spectrum where there is actually data. And this is the reason I stuck with those lines. Of course, we can dilute the spectrum more, but if there are more than those 22 folds of inflation here, the fit to the data is already worse than 3 sigma away. So before we were able to hide the tail, we killed the signal where it matters. And the fit isn't any good anymore. So this also doesn't work, and of course we can also do it well, for the other spectra. For example, this is a red one. You play the same game. You remember that the red one, it was close to 3 sigma by itself. So that's why less e-folds are allowed, because as soon as you modify it even a little bit here, well, it's more than 3 sigma. And then let's say that the fit isn't really good. So for all of these examples, you see that you cannot hide the spectrum from future experiments. Only the game. So there's, yes. This is one of the conclusions. And then, if I have time, am I over time?
That's okay.
Okay. I only have 2 more slides. No, this slide doesn't tell you anything new. This is just, we redid the analysis a couple of months after the first one. So this is the exact same plot than before, but in a slightly different graphics. But this is still GUP. You remember this is exactly the same plot that we've seen before. But the reason we redid this analysis was to do the same analysis for a whole lot of spectra, which are not cosmic strings, and essentially compare various models of the early universe. But what we also included in that particular analysis was supermassive black holes. I'm not going to talk too much about that, but essentially, well, the reason was to try and see how a phenomenological model of the supermassive black holes would change the fits. And the phenomenological model of supermassive black holes has 3 parameters. There's this PV, which basically controls the amplitude of the spectrum, which is what you also have in this, the simplest one, where on the gravitational waves are behind the emission. There is also a slope alpha and then a reference frequency F1, which are supposed to model the interaction of the supermassive black hole binary with its surroundings. And what you can do with those is, of course, do a fit, which is what we did here. But the point is that, as far as I can tell, at least, for astrophysics, you don't really know what those parameters show. There is no easy way to try and check, so the only thing they would do is, again, do the same fit that we do. The difference here is, of course, that we also added cosmic strings to see if having the 2 components, because we do expect there are supermassive black holes out there somewhere, can improve the fit. And the answer is that it doesn't, unfortunately, because so the fit from the supermassive black holes themselves, it turns out, is quite similar to the one from cosmic strings. So as you see, the area that you end up with is bigger because you can essentially make up the missing signal, for example, at lower B by just having the supermassive black holes. So it really doesn't help that much, but it does allow us to try and compare the various models. And this is what this table is doing. Yeah, this is a little bit complicated, but what we're showing here, delta B is the important criterion. So Bayesian information criterion, this is just minus 2 delta likelihood. So this is exactly the number that you would get in your favorite chi-squared analysis. But this is supplemented by number of parameters for a model times the log number of measurements. We have 14 bins. So for each model, there are, say, 2 parameters, 2 times log 14 And this is supposed to penalize models which have more parameters, which is of course what you want to do, because it's quite trivial to have a model which has 100 parameters and fits the spectrum perfectly, but then it's a pointless model. So this is why what this was invented for. And we used this to try and check which models were best. So,
Sorry, so that's the big one. What is delta big?
delta big is changing with respect to supermassive black holes plus environmental effects. So this is, because you see the number is 50 something, so we're just comparing between them rather than giving you the absolute value. Right, but so the models are gravitational waves of supermassive black holes, but only gravitational wave driven evolution. And you see this is not a very good fit, even though it only has one parameter, which is PPH, but compared to supermassive black holes with environmental effects, well, we end up with 6 more B's here, 2 sigma less, something like that. So this is and this will be our benchmark for comparing with the other models. So then, our favorite example is cosmic strings. These are the best fit parameters. And the peak we end up with is actually minus 1.2. So it's very close, not even 1 sigma difference. In the typical say, understanding of those numbers. And the numbers in the brackets, then come from the analysis of combining the cosmological model with supermassive black holes plus environmental effects. So the second, I'll show you again. So from this, we get the number without the bracket, and from this we get the number with the bracket, and the best fit of this model. And as I said, it turns out that this, well, putting those two models together doesn't work. It's makes things worse. 4.6, this is positive, meaning that this is actually really small. Well, but then, unfortunately, it turns out that cosmic strings are not the best cosmological explanation currently, because phase transitions give roughly -5, the range is -5.7, and in fact all the other ones that we looked at, so Steven-Lewis gravitational inflation from standard gravitational waves and all the light ones, they all perform a little bit better than super strings do right now.
What's the first order gravitational wave?
Yeah.
What is the first order gravitational wave?
First order, so this is from. Oh, these are just the primary fluctuations from inflation. This is the only way. Yes, those are inflationary.
How am I supposed to understand your big and delta big? I'm not sure what value should. I'm not familiar with the concept, so.
Not familiar. Right. So
What is a good value? What is the ideal value? 0?
I don't think you can get 0 because so this sort of works, as I said, this is what you would get as chi-squared. So you remember the values for.
Was k log of 14, is that what it is? Was k log of 14?
Yes, this, as I said, this is plus k log of 14, so this would be just the chi-squared that you get. And this is coming from, because the models have different number of parameters. So this is supposed to penalize models that have more parameters. K is the number of parameters in each of the models.
And 14?
And 14 is the number of measurements, with 14 beings in frequency from the pulsar timing arrays. So this is why this is fixed to 14. That's the number we use in the analysis.
So the smaller the big, the better.
The smaller the big, the better. And this does go sort of like chi-squared, so 2.3 would be 1 sigma, something like that. And that is the rough, very rough understanding. So you see that all the other models perform better, but not hugely better. Delta V of 5 is not huge evidence, it's sort of 2 sigma-ish. Better.
You said the numbers inside the parentheses or having taken into account the environment? written supermassive black holes.
So yes, numbers in the brackets are when we try to not only use, say, whatever the primordial model is, the cosmic strings, but also include the supermassive black holes, and then do a fit with 5 parameters, all of those. But in each of the cases, it turns out that, well, of course, you get a slightly better fit, so the chi-squared actually drops a tiny bit. This penalty from 5 parameters, from extra 3 parameters, makes the fit worse.
Yeah, it's gotten, yeah, negative
Yes.
for everyone.
All of them are positive, so there is never a point in thinking of them contributing together. Right, so this is the conclusion so far, but as you've seen, the differences are not huge between those, and as you've seen, with the new data, the slopes and preferred values can still change quite a lot, because the gradient in the resolution is still quite large.
So you would say from this that the best model is just gravitational waves from environmental given supermassive black holes.
Strictly speaking, if looking at the values and domain models, that's what I'm saying.
Yeah, but on top of it, taking into account the environmental supermassive black holes, it's gone up to 2.2.
That makes it worse, yes.
Which, and without the domain walls, the delta big for that one is 0, right?
For this one, yes.
Yes. So by itself, it's a better explanation of the data than if you also take into account domain walls.
No, if you take into account only domain walls, then it's -5.7. So domain walls by themselves are a little better. Not a huge amount of evidence.
Yeah.
So basically, this is very unconclusive so far. Maybe errors are a little bit too big still. But of course, yes, we have to wait to now 1.5 more years for the next, will be 17.5 years, I think, of data taking from the collaborations, and then we'll do the fits again and see if there's more evidence for any of the sources. Okay, this is actually all that I have for
Why
you.
do the domain will act differently from a cosmic string when they're both topological defects? Why would a domain wall act differently to a cosmic string?
Oh, because actually, I do have a plot for this. Because the dynamics driving the production of gravitational waves is quite different in the two cases. And they actually produce a different spectrum. So domain walls, this is the best fit from all of the models. Domain walls are the green one. Actually, the spectrum they produce is quite peaked. It looks nothing like cosmic string spectrum. Because domain walls, I could give another talk on this, but they are essentially domain walls are also topological defects, but those are the ones where they have no internal dynamics in the vanilla model. If you have a potential which is really degenerate, they will just stay around and they will dominate the expansion, and that's ruled out. So in domain walls, what you do is you induce a bias between the two minima, but that causes them to decay at some point.
And that's how they produce gravity.
Yes, it's mostly the decay, and then that's why the spectrum is completely different, because then you have a fixed scale, which is the time of their decay, and that gives you where the peak is. So they don't, they do scale, but most of the gravitational engine actually produces this decay time. So that's why very different. Actually, domain walls, in my mind, are, at least in this picture where they are not degenerate, are more akin to a phase transition. Because the final moments of their existence actually start looking like a phase transition. Right? The different phases realize there is a pressure on the walls and they start accelerating. It does really look like a phase transition value. Cosmic strings which still exist and scale up until today.
Sorry to interrupt. Can you explain again what the basic data that you were trying to explain with this is? I'm missing the essence of the data. It's just the slowing of those pulsars. Is that what the data is?
It's the movement of pulsars.
The separation in pulses, the
Yes.
change in that separation. That's the phenomenon that you're trying to face. And the supposition is that it is gravitational waves of some form that are responsible for that. You're trying to model that.
Yes. Well, but again, this is something you can check, because from gravitational waves you expect a certain pattern in these changes of distances between the pulsars on the sky, and this is something that they're already starting to see.
Is there a competing model that has nothing to do with gravitational waves?
There are too many, because it's very trivial to have something which changes the distance. But that's why this HD correlation is important. Because then that's how they will know that it's not just noise from anything else. Because otherwise those are very unstable systems, right? They move by themselves, you try to clean the data, as far as I understand, the analysis is very complicated. In fact, this is one of the reasons why I keep using nanograph data. This is because nanograph is timing the most pulsars, more than the other collaborations. And you could ask, well, why don't you combine the data? The reason is the different collaborations actually time the same pulsars. So the data is not uncorrelated, you cannot just sum it. And there is an entire body, which is the International Pulsar Timing Array, where all of those pulsar timing array collaborations come together and they try to rehash the data as one big set and reanalyze it together. And they're actually trying to do that now with the data from last summer. And they're still not done, because each of the collaborations has their own ways of data analysis. So then when you take the rough data and try and do the same analysis for all of them, it's very difficult. Well, it's taking them almost a year. So it's really, there's a lot of modeling to do.
Thank you very much.
That's the conclusions, but I think I said all of them at some point. Right, so are there any more questions?
Could you go back to the slide where you were adding up? Yeah, here. What is the reason you take the environment-driven supermassive black hole binaries as your reference? To me, that means you don't really want to throw that away, right? So for me, thinking of domain walls are actually the best fit by themselves is not.
So the benchmark value really doesn't matter. We took this one because this is the one which, well, people working on pulsar timing, they will just tell you that it's supermassive black holes. They don't really care that much about anything else. So for them, this is the explanation, and we're just trying to tell them that this is maybe a little bit better.
Yeah. Can I ask another question? On some of your plots, you had the Tianjin experiment
Yes.
as well, and it was missing on some of the slides. Is there a reason?
There is. It's not a very good reason. It's just that, well, yes, in some of the plots, I remember, yes, this is maybe Tianjin, but it doesn't have a label.
Yeah, but
It is. Well, so the reason is that I don't know. Here it does have a label for some reason. I typically don't put it in because I really don't know what the status of Tianjin is, and no one will tell me. So, depending on whom I was working with when the plot was developed, they told me they talked to someone and they told them that Tianjin is going to happen. They insisted on putting in Tianjin at times.
yeah.
But, well, I don't really have any solid evidence.
What about Desigo and BAO?
Big Bang Explorer,
Yeah.
Big Bang Observer. So this LIGO, well, I'm not putting it in, to be honest, because the plot is a little bit crowded already, and it would be somewhere here. But another reason, well, you just have to make a choice. So the LIGO is also not, as far as I understand, so the lines that people put on their plots don't necessarily have a whole lot to do with the experiment that will end up having, even if the LIGO is realized. Because there are many versions. There's the scaled down B LIGO, which is a little bit more like, not this plot, this is a very old plot. But it looks slightly more similar to our, maybe a little bit higher frequency. But you'll probably, looking through literature, you'll see the results ranging anywhere from 10 to minus 12 to 15 or so. Well, because essentially nothing is certain at this stage. What I know about this figure is that they now have a precursor experiment to some extent. So a Pathfinder mission that will test some of the, there will actually be a satellite testing a whole lot of equipment, and parts of it will be what they envision to use later on the site. But this is still a few years away, and as you know, the LISA Pathfinder mission was already 10 years ago, more than 10 years ago. So it will be a long time before this LIGO is realized. In fact, well, the last I heard, the LIGO was proposed to the Japanese government, and they said no because they are focusing on China right now. So there is, we'll see if it's realized. And with BBO, the story is even simpler because BBO, as far as I can tell, is just one paper. There isn't a BBO collaboration that is actually working. No, there is the Cosmic Explorer one, which is similar to ET, but on ground, 40-kilometer tunnels. Cosmic Explorer, well, there were a lot of studies, and I think they were really pushing to get that realized. But for BBO, I don't believe there is a collaboration actively working. There is one very old paper that people remember and liked, and they got the same sensitivity, but there's no way towards realizing it that I can.
May I ask another question? So on the domain walls, what I know from domain walls is that it's the spontaneous breaking of a discrete symmetry that gives you domain wall.
Yes.
The bound or the result that you have found, how model dependent is it?
The spectrum always extremely model dependent because
So what have you assumed for the results you're showing here?
domain walls. Well, I have to check. So the main thing is the T annihilation, which has to do with delta V. So how we break the degeneracy between the minima, which, as you see, you have to do at a very low scale. And that's when roughly the scale at which the annihilation will have happened. There's this alpha, which I honestly don't remember. But this is, well, so looking at this, there are no favored sets of parameters that you would have motivation for, other than it fits the data. So, yes, you have to unfortunately take it into face value.
Yeah, they don't need to be interacting with each other anyway. They just loses energy.
Domain walls?
Yeah.
Well, they mostly produce gravitational waves once they finally collide and disappear. But it's,
don't they also produce gravitational waves at the phase transition when they go from one unit to another?
no, because I mean, I don't know, but typically in this modeling, you don't even think about this, right? Because there's this, so you have a potential like this, which is just degenerate.
Yeah.
But you don't model the initial transition at all. You just assume that the two minima are populated already. So you could, but then it would really just be a first order transition.
That's what I'm thinking, and I would expect gravitational waves coming from.
That would happen, but again, you don't need this. For the labels, you can just have a second order transition.
Yeah.
Right, but then again, so that would just be extra parameters, because what we have here only has to do with when they annihilate.
Okay.
So essentially, this is the symmetry breaking, right? So typically what you do is you have a potential which has two minima, so not unlike RU1, but with just one field. And then you add, say, plus delta V pretty much by hand to have a bias between the two. And it's this bias that controls when they decay. So then the initial transition when the walls are produced and, well, when they decay, I think will be completely separate. Don't really have anything to do with one another.
And you don't want to add extra complication there, because you will be penalized.
Well, in practice, you can just, add the two together. Because it's a completely separate set of parameters. Because for the labels, you don't care at all about how the potential looked when they were produced. So in principle, yes, you can just add the two. Parameters are still free, because it's only a question of if you can draw a potential that will give you that, and I would assume. Yeah.
Other questions? Any questions on Zoom? No? No. Anybody online has any questions? I am going to stop the recording. Let's back the speaker again.